Okay, it's already 6:05, so let's start. Let me share my screen. Okay, am I audible? Someone can write in the chat box so that I can start. Surgeon, can you write? Are you audible? Yeah, thank you. So, good evening all. Let's start the NPTEL online certificate course, Analytical Chemistry. I am Sohankar from ISC Bangalore, and the course instructor of this course is Professor Devashish Ray from IIT Kharagpur. So, basically, we are almost end of this course. Okay, now week 10 we will discuss. So, basically, in this today class we will discuss about the electrochemical method, whatever we have discussed earlier also. So this is basically the continuation of that earlier course or earlier class only. So basically in this course we already discussed so many things. Basically first we have discussed the introduction part of analytical chemistry, and then different equilibrium method of analytical chemistry. Then along with this we have discussed the spectroscopic method and thermal method. Then we are discussing now the electrochemical method. Okay, so last week what we have discussed, so in this today class we'll discuss on this topic only, the potentiometric titration, what I have already discussed and I have shared the video also. So today also we'll discuss little bit more details of that experiment, and then other things we will discuss, IR drop and electrochemical cell. All these things we will discuss, and metal deposition of some substrate or something. Okay, so basically last week what we have discussed, suppose you dip one copper wire in some silver nitrate solution, then after some time we will see that the solution become pale green and the copper there is some silver deposition is happening. So what basically happening here, so basically if we already discussed the electrochemical series also, that copper is going here, that copper 2 plus. Okay, so that means copper is a strong reducing agent, so that here in the Ag silver nitrate, basically silver is plus oxidation state, so it is going to Ag naught or Ag0. As a result, silver is depositing on the surface of copper. So for this reaction is happening. So this one we have discussed and we have learned. Then we have discussed how we will get or we will make a electrochemical cell. So basically here we learned that if we dip copper wire on copper sulfate solution, and another beaker we have dip silver on silver nitrate solution, and these two beaker is connected with salt bridge. So this salt bridge basically KCl solution is there, and along with this agar agar solution is there, so that the ionic conductivity of these two cells remain constant. Okay, and in these two wire are connected with some voltmeter where you can measure the voltage of these two cells. So from here we get to know the reference electrode as well as or electrode, and how you can measure of these two electrode or electrode potential. Basically E is equal to E right minus E left, or you can write E cathode minus E anode. So all these things we have discussed. So, and what is the cathode electrode, where the reduction is happening, that is the cathode electrode, and what is anode electrode, where the oxidation is happening, that is the anode electrode. So, and from here we learn the Nernst equation, how Nernst equation is derived. That things we have discussed already in the last class. So after that we have learned the potentiometric titration. So I already share two paper on this topic, so it is in the Google Drive, so people can check there, and that is quite interesting paper. So, and after that we have discussed different type of reference electrode. So basically saturated caramel electrode, where we have learned that basically in the glass vial there is some Vicor treat is there, and after that some KCl crystal is there to maintain the concentration of KCl solution. After that, that caramel is there. Caramel basically Ag2Cl2. Okay, so then the mercury contact is there, and along with this the platinum connection is there. So, and this electrode is filled with a saturated KCl solution to maintain the concentration of Cl plus, Cl minus. Okay, so this is known as the saturated caramel electrode, and along with this we have learned about another reference electrode, that is AgCl reference electrode, where there is some Vicor membrane is there. So basically the Vicor membrane is basically maintain the ionic concentration of your inside reference electrode and whatever your analyte on that topic. And this here the KCl saturated KCl solution is there, and one silver wire is there, and silver wire is coated with AgCl paste. Okay, so basically in this electrode the potential of this electrode depend on the concentration of the Cl minus. So for this it is dipped on the saturated KCl solution, so that your Cl minus concentration remain constant. Okay, so these things we have discussed. Now we will learn another kind of electrode, which is known as the indicator electrode. So basically indicator electrode, what the importance? So if this is the indicator, one type of ideal electrode only, which is basically measure the change of the concentration of oxidized and reduced form. Okay, so analyte basically, suppose you are doing some redox reaction where your some reduction product is transforming to some oxidized form, then how the concentration is changing with potential, so that things we can measure by the indicator electrode. Okay, so there is three type of indicator electrode is there. One is metallic indicator electrode, one is membrane indicator electrode, one is ion X sensitive indicator electrode. Okay, so metallic indicator electrode, basically if you do some cyclic voltammetry, or usually when you will do some electrochemical experiment, there are some third electrode or counter electrode we usually call. So that is basically some platinum wire or platinum plate usually we use. So that is the indicator electrode. Okay, and membrane electrode, basically glass membrane electrode usually you use in pH meter or something. So they are basically glass membrane electrode is there. Basically ion can diffuse from one state to another state. Okay, so these things is there. Other things is the suppose you want to measure the potential of some analyte, or some you want to do some measurement where you want to measure the potential of your analyte at initial state, or which we will call OCP, or open circuit potential. So how you can measure that thing? So suppose then you can measure that things with connecting one reference electrodes, that is reference R1. Suppose you are connected with saturated caramel electrode, so which I have shown earlier also, and another electrode you can use, that is glass electrode, that is 0.1 molar AgCl, which is dipped saturated solution, and silver wire dipped on that solution. So these two you can connect it to each other, and these both electrodes are dipped in suppose some ionic solution or some acidic solution, and you want to measure of this ionic solution or some acidic solution potential. What we have learned, that E cell is equal to E right minus E left. So basically if the potential of this cell is E2 and this potential is E1, then you can measure basically the difference of these two cells. Okay, so E2 minus E1. So basically these things is there, and then membrane electrode, basically we have measured, as I have already told, that pH electrode, basically a membrane electrode or glass membrane electrode. So basically pH meter, where you can measure the difference between the concentration of proton, or which is depend on pH. So basically minus log of H plus concentration. So the difference of two solution with different concentration of hydrogen. Okay, so these things you can measure by pH electrode, and this pH electrode basically the term which we call p ion electrode also we call, and all the concentration that we represent in pH, or suppose you are measuring the concentration of calcium, then you can represent as pCa, or nitrate ion, then you can present in ApNO3. Okay, so these things is there. Then after that, what we have discussed earlier also, the potentiometric titration. So potentiometric titration, basically we are measuring the potential with some analyte adding in your solution. So basically this is the potentiometric meter instrument. So basically last video what we have learned, see that one electrode, this kind of electrode is there, which is not connected with the instrument, but it is some router kind of thing is there, which is Bluetooth connected, and it can control by the software. But this is the similar kind of instrument only. So basically it is connected in the instrument and by wire, and it is there two type of bottom is there. One is you can measure the pH of the solution, as well as you can measure the potential of the solution in millivolt or volt per unit. And after that, the experimental setup is like this. So you can take one beaker, and on the beaker, suppose you have some mixture of some halide solution. Suppose you have given some analyte which have contained chlorine minus and bromine minus and iodine minus, and you want to measure the concentration of chlorine, bromine and iodine. So you can measure some indicator also, but here the potentiometric titration no need any indicator. You can measure the potential change of the solution by adding the analyte from the burette. So basically in the burette you are adding the silver nitrate solution, which is a secondary standard, and this secondary standard can be standardized by KCl solution, so that the concentration of the silver nitrate you can know, and after that you are adding the silver nitrate solution in the analyte, and what will happen, silver Ag plus, and in the solution you have chlorine minus, it will form silver chloride, white precipitate. Okay, and along with this bromine also, silver plus, it will react with bromine minus, it will form AgBr. Okay, now which one will first precipitate and which one is last precipitate, that depend on the solubility product. So compound have a higher solubility product, they have precipitate at the end. Okay, so in this there is the magnetic stirrer, so you can mix the or stir the solution along with time, and you can drop the what is called solution and from the burette, and you can measure the what is called pH of the potential of the solution. Okay, and in this measurement, what you can measure the neutralization reaction. Suppose some acid base reaction is happening, in that case you have measured the pH of the solution, or change of the solution, change of the pH of that solution. And then other things is precipitation reaction, what I am discussing here, that suppose you have some precipitate happening of some bromide or chloride ion, and that reaction also you can measure in this setup. And another thing is some complex reaction is happening. Suppose iron 2+ is there, and you want to measure some phenol-3 complex O10 is complex formation is happening, and this case also you can measure with this experimental setup, and some redox reaction is happening, and that case also you can measure this thing. Okay, so last class what we have see that if you have some three mixture of this solution, how is the graph like this? You are measuring the potential of this y-axis and this here volume of silver nitrate, and the graph is like this initially. So basically three type of things is there, where you have chlorine mixture, bromine mixture, and iodine mixture is there. Okay, so basically here you get some volume. Suppose this one is V1 and this is the V2 and this is the V3, and KSP value of this halide and order is iodine is very less than bromine and then chlorine. Okay, that means iodine can precipitate easily, and first whatever hump is there, this is for the iodine, and this one is for the bromine, and this one for the chlorine. Okay, now question, how we can get exactly the volume of this solution? So for this we have to do the first derivative of the solution of this volume. So basically we have the potential, so E versus V, so volume of the silver nitrate solution, then you will get some P. So from there you can get the exact volume of the solution. Okay, how much silver nitrate is required to precipitate iodine completely in the solution. Okay, so suppose you have to get two hump of this solution very close to each other, then that case you can do some double derivative of the solution also. Basically double derivative of potential versus volume of the silver nitrate. As a result you get the exact volume of silver nitrate solution. So basically we have learned in 10 or 12 standard that V1 is V2, V1 S1 is equal to V2 S2. So basically you know the concentration of silver nitrate here, and volume, how much volume is required for precipitate silver, what is called iodine, or sorry, so silver nitrate, how much volume is required, and after that here you know how much volume you have taken. So basically suppose 10 ml of the mixture solution is you have taken, then from there you can get the concentration of iodine minus, so how much iodine is there in the solution. Okay, so and in here basically whatever your solution is there or analyte is there, more than that whatever analyte you have taken in the burette, that concentration is higher, because the error bar of this experiment will be very low. So after that what we have discussed, that if you are doing some redox reaction also, that case also you can do this type of reaction. Basically you can measure the potential change of the titration, and that case you can measure the concentration of the analyte. Okay, so basically suppose you are doing some redox reaction, suppose Fe2 plus analyte is there, and you want to measure the concentration of the Fe2 plus in that analyte, then you can do some redox titration, basically can, or which is known as serate ion. So basically cerium 4 plus is there, and in the aqua solution you are doing, so what will happen, the cerium plus, which is a strong oxidizing reagent, so it will trans itself reduce to a cerium 3 plus, and oxygen what will form Fe3 plus is formed. Okay, so On the other hand, suppose you are doing some cerium with the uranium, which is very important. So uranium 4 plus where cerium 3 plus you are doing with aqueous solution, what will happen? Uranium O22 minus where plus 6 oxidation state, sorry, plus 6, not plus 6, plus 5 oxidation state it is going, and cerium 3 plus and 4H plus is happening. So basically if we plot these two reactions in one graph, then what will happen, where you are measuring the potential change of the reaction and volume of cerium. So what you will get, so this is this equivalent point for the Fe2 plus, and suppose that for cerium it is coming like this, and here you will get for uranium 4 plus. So basically here you will get the volume of the cerium 3 plus, and from there you can, this is cerium 4 plus, so from there you can get the concentration of Fe2 plus as well as uranium 4 plus. Okay. So after that, what we will discuss, the redox reaction. So basically here some indicator usually used. What is there? There is two type of indicator is there. One is general indicator, one is specialized indicator. So general indicator basically it will show some color in oxidized or reduced state. And potential specialized redox indicator, what is there? So specialized redox indicator basically it will react with electrode as the result some redox reaction happens. Okay. So when we will discuss this auxiliary or auxiliary redox indicator, so basically there is, what is the meaning of these things? I think yeah. So basically when it is react with the some compound and it is transform the redox reaction and it is formed, I forgot where my cursor, yeah. Okay, so basically what is there, so suppose you are reacting with some manganese solution, suppose manganese 2 plus is there and it is reacting with sodium bismuth oxide. So what is there, so this manganese oxide with reacting with sodium bismuth oxide, it will form MnO4, which is a highly oxidizing agent, and NaBiO is formed. So as a result this one will precipitate and this one you can filter it from the reaction, and this KMnO4 is there, so or NaMnO4 is formed, so which can react with Fe2 plus to Fe3 plus, so some redox reaction is happening. So as a result you can get the you can get the equivalent point for Fe2 plus to Fe3 plus reaction. Okay, so this reaction you can do another things is there. The bulk electrolysis, basically what is there in the bulk electrolysis. So whatever we are doing in the electrochemistry or cyclic voltammetry, that all the reaction whatever is happening on the electrode surface, so we are not considering on the, or I can say, the bulk solution. But in this case bulk electrolysis, basically whatever current you are applying in the cell, and that cell whatever electrodeposition or something is happening on the bulk solution also. So in this electrolysis, basically bulk electrolysis, basically electrogravimetric analysis or colorimetric analysis usually used to do. So in that case, basically electrogravimetric analysis, what is there? So electrogravimetry, basically gravimetry means you are measuring the change of the mass of some analyte, and there is electro, that means you are applying some or you are transferring some electron. So due to the electron transfer, some chemical reaction is happening, and due to that some mass change of the electrode is happening, and as a result you are measuring how much current or coulomb charge is required to change the gravimetry or change the mass of your electrode. So basically in this case you can measure the potential of the cell, but as the change of the mass or whatever things your electrode mass is changing, so basically whatever potential you are getting, that is not the exact potential. So basically what I want to say, that in the Nernst equation you have discussed that E cell is equal to E cathode minus E anode. So basically you have taken one beaker or some cell, and there is some electrolyte, and you have taken two electrode, one is anode and one is cathode. Okay, so on the anode and cathode, whatever reaction cathode, some reaction is happening. So and you are measuring the potential. So at early school days you learn that whatever some reduction is, if some reduction is happening on the opposite reaction, that is oxidation is happening on the other electrode. So in that electrode some oxidation is happening. So as a result, as the reaction is happening on the electrode surface, whatever potential you are measuring, that is not exact potential. So for this usually we introduce another electrode. So if I draw here, suppose you have some cathode, or you can say working electrode, and here you have another electrode which we can say that reference electrode, where in respect to this reference electrode we are measuring the potential, and other one is the counter electrode. Okay, so basically what is the function or what is the importance of this counter electrode? Basically here the counter electrode, basically what you are doing, you are transferring the electron through this counter electrode and working electrode. As a result, whatever reaction is happening, or I have told that the reduction is happening on the working electrode or what is called cathode, and some opposite reaction, that is reduction or oxidation, that is happening on the counter electrode. But you are measuring the potential in between reference electrode and the working electrode. As a result, what you are get the potential, that is exact potential. So now question, why this potential is not getting, or whatever we are measuring in two electrode cell, whatever potential we are getting, that is not exact. There is two types of potential deviation is there. One term is called IR drop, and other one is polarization. So basically IR drop, what is this IR drop? So basically IR drop, basically what is there? IR drop I can discuss here. So you have taken the solution in your beaker and you are measuring the potential. So whatever the solution is there, due to the solution property or ionic strength of the solution, ionic strength of the solution, whatever current you are getting, so there ion movement is there. So this ion movement, when one ion is going from the reference or bulk solution to the electrode surface, due to the solvent property it is feeling some resistance. So this resistance is known as the solution resistance. What you can measure here in the picture, you can see that the R value is showing 15 ohm. So basically this is the solution resistance. So due to this solution resistance, however potential you are getting, that is not the exact potential. So due to that, whatever current is getting, so that current along with this potential resistance is known as the IR drop. So in this resistance, how you can measure this resistance? That you can measure from the impedance spectroscopy. So here I think there in this course impedance spectroscopy is not there. So I will introduce a little bit how the impedance spectroscopy looks like. So these things I will discuss a little bit later. So basically IR drop, whatever cell you are measuring, so from there or applied potential, so basically minus E cell minus due to the IR correction, some potential deviation is there. So another one what I have discussed is the polarization. So polarization, basically this is basically electrode property. So basically electrode properties means when in the working electrode surface some reaction is happening, due to that if there is some deviation of potential, that is from the thermodynamic potential. So what is the meaning of this sentence? Basically suppose you are doing some reaction or some suppose potential and you are measuring with versus time, then you will see when the reaction is happening, suppose it is happening at this potential, suppose 2.5 volt, but the thermodynamic potential of this reaction is 2.9 volt. Okay, so whatever deviation is there 0.4 volt, this is known as the polarization, and this polarization can come from the anode as well as cathode. So as I have this mentioned that this polarization is due to the electrode properties or due to the electrode reaction for this. So this whatever polarization is coming, this contribute from the anode as well as cathode. Okay, so this IR, whatever I have discussed, that this resistance you can measure from the impedance spectroscopy, or whatever I can say the polarization also you can get some information from impedance spectroscopy. Basically what we have learned from Ohm's law. So basically you have I and you have V. So if increase the potential, it will be like this, and after that it will deviate it from the ohmic what is called behavior. So and if it is like this, so from here whatever things deviated, so if we draw a line where it is started from deviated, so whatever potential deviation is there, this one, so this one known as the polarization. Okay, so polarization is there, and as it is deviated from the IR or ohmic behavior, so basically Ohm's law, we know that V is equal to IR or E is equal to IR. In this case, in electrolytic cell, this IR is not which is known as resistance, is not a pure resistance. Okay, so because in the electrolytic cell there is some solvent resistance also there, as well as from the electrode reaction is happening, due to that the charge transfer resistance also there. So all these things is there. For this R we usually write, that is known V is equal to ZR. So this Z is known as the impedance. So this Z, there is two part. One Z is equal to Z prime minus or plus IZ double prime. Okay, so this is the imaginary part and this is the real part. Okay, so basically if you plot Z minus Z double prime minus Z, which is, sorry, you can draw here minus double Z, which is ohm, and Z single prime, which is known. So there is two type of presentation is there. One is Nyquist plot, basically minus Z versus Z prime, that is Nyquist plot. Other one is Bode presentation, basically you are measuring the what is called resistance as a function of frequency. So if you plot in Bode, so which kind of this kind of graph will come. So basically this one known as the solution resistance, or whatever we have discussed here, the IR resistance, IR drop or something, and this one is known as the charge transfer resistance. So which is basically the get the information about the polarization. So with the reaction, if you see that with time or with reaction the polarization is increasing, that means if you do with time the some impedance spectra, then you will get to know that it will like this, some charge transfer resistance will increase. So basically you can see that your R value or resistance value is increasing with time. That means with time whatever chemical reaction is happening, with that the charge transfer resistance or polarization is increasing. So this information you can get from the impedance spectroscopy, which is a very vast topic. So now researchers what is called working on this impedance spectroscopy to know different type of transistor or polarization property of different compound. Okay, so these things is there, and along with this what we have discussed, that electrogravimetric method, basically you are doing some electrochemical reaction, and along with that we are measuring the change of the what is called the mass of your electrode. So that things is there, and then working electrode of the cathode and where the analyte is deposited at the metal, as what I have discussed also. So basically now we are discussing here that you have taken a electrochemical cell where 3 electrode setup. So basically you have taken the working electrode and as a reference electrode, and another one is counter electrode, and your analyte you have taken in the beaker or electrochemical cell. And you are measuring the what is called potential in the reference and working electrode, sorry, working and reference electrode, yeah. And this key circuit which is known as the reference circuit, and another one you are taking that you are measuring the current, so in between the working electrode and the counter electrode, and which is known as the electrolysis circuit. Okay, and in this some DC power source is there where you are applying the key current, or you are key in the working electrode. So now we will discuss about the metal ion deposition. So basically, suppose you have taken different what is called ion mixture, and you want to deposit on some substrate or some other metal electrode surface. Then what you can do electrochemically, you can do the metal deposition on that metal substrate. Basically, suppose you have taken some iron, what I have shown that the copper rod you are deep in the silver solution, silver nitrate solution. So basically silver is depositing on the silver nitrate plus. So basically what you can do, you can apply some potential at a particular ion redox complex where silver Ag plus is going to Ag naught or Ag 0, and if you keep the potential of that cell at that potential, then what you will see that silver is depositing on the copper substrate. So these things is there, and on that basis, so there is some potential of with respect to the reference electrode, and this what is called yeah. So basically this potential whatever is versus AC, that is not a standard potential. This is what is called some IR compensated potential, because we already know that due to the solvent and the electrode properties, there is some potential deviation is there, and due to that whatever potential here it is representing, that is not a standard potential. So if you want to deposit of this ion on other substrate, then you can see there is some potential minus 0.6 for tin, and for copper minus 0.3 volt. So you can deposit copper on some other substrate, then you have to keep the electrode potential on minus 0.3 volt if you want to deposit the copper on some electrode surface. Okay, so other key method is that coulometric method. So basically coulometric method, what we used to do, we used to measure the charge of some redox reaction. So basically you charge, basically you are quantifying the electrical charge required to convert a sample from an analyte quantitatively to different oxidation state reaction. And from the Faraday rods, as we know, so how much quantity of charge is required to convert 1 mole of solution or one equivalent of analyte, So basically what we know that Faraday's law, that is Q is equal to N F, or what I can rearrange this, N is equal to Q by NF. Yeah. So basically this N is the number of mole of the analyte, Okay, and q is the charge, how much charge is required to transfer of that reaction, and af is the Faraday constant, and this is 96845 coulomb per mole. Yeah, Rn is the number of electron. Okay, so this is the Faraday laws, where you can get to know that how much charge is required to convert 1 mole of any solution. Okay, so basically suppose you want to convert silver, so basically the coulomb is charge required to produce 0.001118 gram of silver metal from the silver ion. So basically the molecular weight of silver is 111.8 gram per mole. So from there you get to know that suppose 1 mole of silver, which is a 1 electron process, and you get to know that okay, 1 Faraday what is called 1 Faraday of so Na basically Q, and you know this is a 1 electron process, and Faraday 96845 is there. So and this is the gram of what is called silver. So silver molecular weight is this, so 0.00118 by 118. So basically you get to know from here that how much charge is required to transform this much of silver from silver plus to silver. So all these things, I think it is there. Other, I think I have discussed all the things. Now we can discuss some question of this topic, so that we get to know more details of this topic. What is the question is there, and let me see. Yeah. So what are the criteria for secondary reversible electrodes? So there is 4 options. I will wait for 10 or 15 seconds. So you people can answer in chat box. I think I have to check what is there in chat box. Okay, Sarjan Singh is written that how glass electrode is used for measurement of Ag plus and Na plus, since it is mostly used for measurement of pH. Okay. No, glass electrode. Yeah, glass electrode is used for the what is called pH measurement only. So precipitation, there is in the instrument you can transfer the what is called pH meter, and there is 2 options basically, E potential and pH. Okay, so whatever things you want to measure, the instrument can transfer the value of that what is called analyte only. So basically what you will measuring the Na plus and silver plus. So basically in this case you have to do the precipitation reaction. Okay, and precipitation reaction where you can measure the potential change of the reaction. Okay, so potential change, because when what is called Ag plus is there in the solution, where I have shown in the burette, and in the what is called okay, and in the solution what you have there in silver what is called chlorine halide ion is there, so this will precipitate. So due to the precipitation, whatever ionic what is called conductivity of your solution is changed, as well as your potential what is called of the solution also will change, because in the whatever electrode you are taking, in that electrode 2 electrode is there, one is reference electrode as well as what is called working electrode is there. So I think last class also I have shared that paper also, that you are measuring the reference electrode, and one what is called copper wire is there, and in that copper wire and your reference electrode you are measuring the potential. So the in sodium and Ka plus you have to measure for potentiometric titration only, not pH or what is called, yeah, pH titration. So that is potentiometric titration. So what are the criteria of secondary reversible electrode? So it should be chemically reversible, thermally coefficient of potential should be small, and the potential must remain almost constant when small current passes, and all the above. So if people can write in chat box so that I can track. Okay, so basically secondary reversible electrode, basically whatever things is there, that I can take one example, that AgCl electrode, which is a secondary reference electrode or reversible electrode. Basically what is there, so on the silver wire is there, and on that surface silver AgCl electrode, what is called AgCl coated is there, and which is deep on the saturated KCl solution. So basically in this case here AgCl, which is a solid, and silver also solid. So what is happening here, AgCl and it is called KCl also there. So Ag naught plus Cl minus is there. So if you write Nernst equation, E is equal to E naught minus RT by NF ln AgCl, it is called product minus Ag naught and Cl minus by AgCl. So as this is solid, so the activity of the solid product is 1, and Ag naught, this is also solid, so this activity is 1, and Cl minus, only the Cl minus, so the concentration of Cl minus is there. So that means on the electrode surface, the Cl minus on the electrode surface and Cl minus on the solution, there is some reversible change is happening. So that means it should be chemically reversible, what I have mentioned, and the as this is a reference electrode where the reaction is separated from your analytic, and all this reaction is happening at a time. So for this, the potential of this electrode also remain constant. So the answer is D, that the potential of the electrode remain constant and it should be chemically reversible. So what is the correct statement for a glass electrode? So it is an ion selective electrode. It is commonly used for pH measurement, and glass electrodes are sensitive to single charge ion. All of this, I think just now I have discussed, so you people can I think easily answer this question. So basically what I have discussed, I think time is almost over, so I can discuss all the questions very quickly, so we can complete the discussion in time. So basically glass membrane electrode, what we have discussed, that we can measure 2 proton concentration of solution H plus, so different concentration of proton is separated, and this proton ion concentration, due to the difference of the proton concentration, we are measuring the potential of the electrode by membrane. So okay, what I have discussed also, that it is commonly used for pH measurement. Yeah, this is also correct, and it is ion selective because this proton whatever membrane is there, so in through this membrane only H plus can pass from higher concentration to lower concentration, and this glass electrode is sensitive to a single charge ion. Yeah, so these three is the question. So what anion is detected by sodium thiosulfate as a titrant? Okay, thiosulfate. Okay. So which anion is detected by sodium thiosulfate as a titrant? IO4 minus, chlorine minus, sulfate minus, and none of these. Okay, I can discuss. I think so. Basically, which anion sodium thiosulfate? Basically, sodium thiosulfate, it can stoichiometrically react with iodine. So basically, when we will do some iodometric titration, that case basically we usually use sodium thiosulfate. So basically, sodium thiosulfate is what is called transform. Sodium thiosulfate, I think there is Na2H2O3 H2O. So basically this is the thiosulfate what is called thiosulfate formula. So it is phthalate, tetrathalate is formed, and with reaction with I2 iodine. So the AgAgCl means silver chloride, and chlorine and cadmium to cadmium. So which is the reference electrode used in the above cell? So silver chloride electrode as a reference electrode, or cadmium chloride as a cadmium as a electrode, reference electrode, or hydrogen electrode, or platinum electrode. So this is the what is called cell. So if you present this cell as a cell representation, then what you can represent that cadmium 2 plus is going to cadmium, and it is separated by salt bridge. Then AgAgCl solid, what is called chlorine minus, this is aqueous solution. After that Ag plus and AgCl. It is in solid. So as you know, then if you measure the cell E right minus E left, so this is your one electrode and this is another electrode, and this chlorine is your analyte. So basically this AgAgCl as a what is called a reference electrode, what we have discussed already, and here cadmium is going to cadmium naught or cadmium zeros. That means the potential of the cadmium is changing. So what you can see that silver chloride you can use as a reference electrode. Okay. So what do you mean by IR drop? So it is potential difference, it is current difference, it is resistance difference, and it is what is called concentration difference. So I think I have already discussed. So what it is there, you are measuring I versus B, and it is coming like this. So basically whatever deviation is there, suppose this one, so this is the deviation of potential. So it is the different potential difference, because you are not measuring the current IR drop, so V is equal to IR. So this is the potential, so this is the potential difference. The resistance difference we are not measuring, because it is called at a particular potential you are measuring, and if you are measuring with time, then it will be like this. So at a particular time you are measuring resistance, so this is not the resistance difference, and it is a concentration difference. So basically it is not a concentration difference, so the answer is A. So what is the principle of electroplating method? So electroplating means you are depositing or some metal on from oxidations, some oxidation state to 0 or metal 0 state. So this is the electroplating, that means your electron transfer reaction is happening. So deposition of one metal over another metal. So I think this is on answer, and it based on the theory of hydrolysis. So hydrolysis basically what is called, if you do some the electrodeposition reaction in aqueous solution, then what is called water can react with other substance, and among with this some decomposition reaction is happening. So that is what is called hydrolysis. So in this case also there is some final product water is formed. So this is also one answer. Deposition of paint over non-metal. So this is not the correct answer. So both A and B is the correct answer. So what happened when the electrodeposition of copper and what is called tin mixture occurs in presence of tartarate ion on the cathode weighted platinum? Okay. So what happens when the electrodeposition of copper and tin mixture occurs in the presence of tartarate ion? So basically here what is there, so copper also +2 oxidation state, and SN tin also +2 oxidation state is there. So if you what is called write in tartarate, so basically tartarate, what is the formula, that yeah, acid I think. So basically if you mix, you have these two mixture, so this tartarate anion, it is easily react with the SN K2 plus, as well as if it is some oxidation reaction is happening and tin is formed SN2 plus to SN4 plus, and this anion also react with the SN4 plus also. So as a result as it is reacting with the anion, it will be in the solution state. So only the copper which can transform copper to +2 copper not. So as a result copper can deposit on the platinum substrate. Okay, so the answer is B, what is called copper is deposited on platinum substrate. So which indicator is used in determination of cerium in titration of cerium sulfate with sodium oxalate? Which indicator is used in determination of cerium in the titration of cerium sulfate with sodium oxalate? 4 options is there: ferrium, methyl red, methyl orange, and none of these. So what is called ferrion can use basically ferrion sulfate whatever is there. So basically this phenolphthalein complex which is known as O10. So Fe2 plus is there, so which is a pale blue in color. When it will oxidize Fe3 plus O10, I think this is 3, this is 2 plus. Okay, so this is red color, and along with this the potential also will change. So okay, and for this the ferrion, which is the complex in this complex name, this is ferrion. So this one will happen when some potentiometric titration you are doing and you are present in the cerium complex. So basically cerium is transforming from cerium 4 plus to cerium 3 plus. So basically this is a one electron process, and this methyl orange and all these things. What is this? Yeah, methyl orange, and what is this? This is the pH titration indicator. So which one the incorrect statement of potentiometric titration? So it is similar to direct titration of redox reaction. Here indicator is used. In this method, potential is measured and measured itself with the addition of titration. So basically what we have discussed in potentiometric titration, that you are taken some canalite and you have some electrode, and you are from the burette you are what is called adding the titrant. So basically you are measuring the potential of this reaction. So and in this reaction you can measure neutralization reaction, also precipitation reaction, and redox reaction, and what is called precipitation reaction and redox reaction and neutralization reaction. So the if you are doing some redox reaction, that means you are also measuring the potential with direct adding of the titrant, or and if here no redox indicator usually you did not use, because you are measuring the potential. And if you measure the potential with potential, if you plot the volume of the solution, then you will get a sudden jump of the potential, and from there you will get the equivalent point of your reactant. Okay, so this the incorrect statement, whatever it is there. So there basically you did not measure the what is called adding the indicator. So which one is used as a oxidizing agent in the redox titration of cerium 4 plus, hydrogen peroxide, lithium aluminum hydride, hydrazine, or seric ammonium nitrate, or what we can say this is known as a can. So the answer is seric ammonium nitrate. So basically what is happening in seric ammonium nitrate, when uranium 4 plus is there and you are taking cerium 3 plus and of water molecule. So basically uranium 4 is formed. I think I am doing some mistake. So which one is used as a oxidizing agent in the titration of uranium 4 plus? So basically uranium 4 plus, yeah. So uranium 4 plus plus cerium 4 plus. So what will there? 2H2O, 2O22 plus 2 cerium 3 plus 4H plus. So this is, yeah. So the answer is D, ferric ammonium nitrate. Okay, so thank you all. I think this all the answer. Uh, I think almost all the things is there. So thank you all. I think if you have any question, then if you can ask, or you can write the inside in the chat box. So I think I am almost over. So if you have short question, then I can discuss, and after that I can call up the meeting. Okay, if you don't have any question, then okay, thank you all for joining, and let's call up the meeting. We'll meet next week, and we'll discuss, and we'll continue on the electrochemical method only, and more details of different electrochemical technique, so that later we'll application part of the electrochemical method, then we'll